Okay, yeah, thanks everyone for turning up. Also thanks to the GA Pathways team for inviting me to give this presentation. It's a real honour for me to talk about plate tectonics because it really is one of the fundamental processes that shapes things that happen in, within, on and around the Earth. And also it actually underpins a lot of the work that we do here at GA. So many of you would have heard probably the basics or even heard the term plate tectonics all the way back when you were in high school. So you may have a bit of an idea about what plate tectonics is. But hopefully by the end of this talk you'll sort of have maybe a more robust understanding. A bit of a preview is that it doesn't really operate like this. Okay, so before we get into plate tectonics, or the theory of plate tectonics and what it involves, just a couple of fundamental concepts that I think we need to sort of understand so we're all on the same page. The first one is the structure of the Earth. And so many of you will know that going from the centre of the Earth outwards, the innermost part is the core, and in the core, the centre of the core, the inner part is the inner or solid core. That's surrounded by a liquid part, the outer core, and there's a movement of the outer core around that solid inner core of mostly iron and nickel that generates our magnetic field. Moving outwards from the core, we have the mantle, and the mantle makes up most of the volume and the volume of the Earth, and that extends all the way nearly to the outside of the Earth. And then right at the outside we have the crust. This is what we are standing on at the moment and is what underlies all the continents and also the oceans and the ocean basins. Now the crust and the outermost mantle are the most rigid part of the Earth, and they form what's called the lithosphere. And this is what's broken up into those different plates, or the different tectonic plates that we're going to be talking about. The second concept that I want to get across to you guys is that there are two main types of crust on the Earth. The first is the continental crust, so that is what we're standing on, sitting on, building on at the moment. This is generally thicker, it's generally quite old. It has a composition that's quite similar to granite, so many of you will have seen granite on workbenches or a lot of the things like gravestones, for example, quite a hardy rock. But the key thing is that it has a relatively low density for most of the rocks that we see on the Earth. And that's a typical example of granite. You can have a look at that after the talks. I think Steph will also talk about that as well. Now, oceanic crust, on the other hand, that underlies most of the major oceans on the Earth. That is generally thinner, about 7 to 10 kilometers thick. It's a lot younger in general than most of the continental crust. This has a composition that's very similar to basalt, so that black, very dense rock that you may have seen if in many cities they form the paving stones or other building stones. Melbourne, for example, if you walk around the CBD, you'll be walking on a lot of basalt. And like I said, has a higher density than granite. So we'll go through again why this is a bit more important later on. And you can have a go at hefting or sort of weighing these samples to see if you can tell the density difference between those two rock types. They're available after the talks. Okay, so what's the big deal about plate tectonics? Why is it important, and how did it come to be the major sort of theory that underpins a lot of Earth processes? Well, the surprising thing is that it's a relatively modern idea. There were some early ideas from the 16th century about how continents moved around, but it wasn't really fully accepted by geologists and the wider scientific community until the early 1960s. The modern theory was developed in the early 20th century by a guy called Alfred Wegener. Now, he was not a geologist, he was a meteorologist. So if you need some inspiration for innovation, this guy set the bar really high. So he basically condensed and formulated a lot of evidence into a theory, an early sort of precursor theory to what we now call plate tectonics, and that was called continental drift. Now, I'll just go through some of the evidence that he sort of pulled together. There are lots of different lines of evidence, but here's some of the main ones. Now, the first one is that people had looked at the outlines of the continents after we've sort of been able to map and image what the Earth looked like sort of over the last few hundreds of years. And people started looking at the shapes of these continents and thinking that they were almost like a jigsaw, some of them. You can almost see some of them fitting together if you move them around. And so South America and Africa are two of the best examples of this. And people think that around 200 million years ago, they fitted together like this and have now drifted apart to their current position. The second line of evidence for continents having once been sort of together at some point and moving apart are when we look at the types of rocks that we see on the edges of these continents today and also their ages. And a lot of them are very similar. They're now on very distant continents, but they have the same characteristics, the same ages, which leads us to believe that they might have been once connected together and again have drifted apart. Other lines of evidence, going back to Tegan's talk of paleontology, is when we look at the distribution of fossils. So we're talking exclusively now about sort of land fossils, the ones, or land animals, the ones that couldn't fly across continents, so they would have had to have sort of walked everywhere. We find a lot of fossils, or similar age fossils in rocks, that are, again, across now very distant continents. And the most elegant explanation for this is that they were once joined, or the continents were once joined, so the animals could freely move across those continents or land bridges, and when they died, they deposited their fossils into those layers and beds, which are now separated by vast oceans. And there are other forms of evidence, things like glaciation and other things. Okay, so Wegener's ideas weren't really accepted until the 1960s, and it really took off quite quickly after that with advances in technology when we were able to map the seafloor, and in particular looking at things like the age of oceanic rocks. So when we look at the magma that comes out of what we call spreading centers, I'll go through these in a minute. So this is where we have plates diverging, magmas being extruded into lava and deposited onto the oceanic crust. We see that it's sort of symmetrical, it sort of forms symmetrical patterns away from those ridges. So it's suggesting that we've sort of seen a spreading of those plates. And what really sealed the deal was when we were able to date the ages of those rocks coming out when they had cooled down, and to age them using things similar to what we do here at GA using the shrimp. And what happened is you can see the red colours are ages of oceanic rocks that are very young, and the greens and the blues are much older. So when you move away from these areas that are creating new magmas today, we see the ages getting older and older and older the further you generally get away from these ridges. And also the oldest rocks that we've dated from the oceanic basins is about 190 to 200 million years old. At the same time, or sort of similar time, geophysics or geophysicists were starting to image what happens away from these diversion margins, and seeing what happens when the oceanic crust actually subducts. Remember, it's a lot denser than the continental crust. Where we have oceanic crust meeting continental crust, it's always the denser oceanic crust that subducts, and these are what's called subduction zones. And we were able to start imaging things like earthquakes, what depth they occur at, and eventually being able to image the actual subducting slab going down into the mantle. And then finally, more modern techniques such as GPS, global positioning, we were able to see actually the movement of individual continents on the Earth's surface. And the main reason why people had a bit of a struggle to rationalise or accept plate tectonics was that there wasn't really a mechanism that was available to explain what was going on. And eventually we now understand that in general the main process that's driving plate tectonics is mantle convection. So it's in its simplest sense, we have hot material rising at some point in the mantle. Some people think it starts sort of at the core mantle boundary. The hot material rises, it drives apart those mid-ocean ridges, as it cools, it sort of comes back down and helps to drag down those oceanic crust in those subduction zones. So here's a sort of overview of a large region of the Earth here. We can see that the crust, or the lithosphere, is created at those mid-ocean ridges or spreading centres, and it's sort of destroyed or recycled back into the mantle at subduction zones there. So you can think of the whole process like a conveyor belt, where we have the mid-ocean ridges, these things here, forming new crust, and subduction zones returning that crust back down into the mantle. So here's what here's our best understanding of what the current tectonic plate framework is on the Earth. All those sort of stitched lines you can see there, so the best example is perhaps in the Atlantic there, the Mid-Atlantic Ridge. Those are those spreading centres, so plates moving apart, creating new crust. And those lines with the barbed lines, or the ones with the triangles on, those are those subduction zones where we're seeing the subduction of the oceanic crust, either beneath other oceanic crust or beneath the less dense continental crust. And there are some examples of the plate tectonic jigsaw plates that we've got from the Ed Centre, which you can have a look at and play around with and try and fit them together afterwards. Now, the cool thing about plate tectonics is that it hasn't always looked like this, and we can use various lines of evidence to sort of back calculate what has happened to the plates in the past and how they've come to form their current configuration. So I'll just show you one of the reconstructions from around 300 million years ago to the present state. So see if you can track what's happened to Australia. It's actually started down here, so it's this purple area here, and we're starting at 300 million years ago. So this is when we had all the continents were sort of joined together to form what we call Pangaea, and the southern part of Pangaea you might have heard of is called Gondwana, or Gondwana land. So let's play this and you can see what's happened. So getting to the age of the dinosaurs now. Okay, so it's time for your red and green cards, and we're going to play Plate Tectonics Price is Right. So the question is, how fast, on average, how fast do tectonic plates move? Okay, so the first one is, do you think they move faster or slower than glaciers? So if you think they move faster, hold up your green bits of paper. If you think they move slower, hold up your red. Okay, yeah, mostly red. So red is the correct answer. So glaciers move on average about 1 meter per day. It varies, but that's about the average. So tectonic plates move slower than that. How about a snail? So again, do you think they move faster or slower than snails? Snail pace. Great, I think, yeah, red's the overwhelming majority there. So snails actually move on average around 47 meters per hour. That's pretty quick, right, for snails? Okay, how about how fast your fingernails grow? Faster or slower? Yeah, that's pretty much 50-50, and it's actually around around the speed that plates move. Some are a bit faster, some are a bit slower, but in general, how fast your fingernails grow, that's about how fast most tectonic plates move. That's around 4 centimeters a year. It varies between about 2 and 10 centimeters a year for tectonic plates. Now, Australia is on, I've got an example here. So Australia sits on the Indo-Australian plate. So Australia here, India here. We think perhaps there may be a bit of rupture between India and Australia somewhere in the Southern Ocean there. It's one of the fastest moving plates, and Australia is actually probably the fastest moving continent on Earth. And that's moving at about 7 centimetres, pretty much north per year. And we'll come back to why this is important in a second. So here you go, here's that same image. And now if you have a look at these green arrows, you can see that the direction of these plates are moving, and the length of those arrows dictates how fast they're moving. So here you go, here's the Australian plate here. It's moving pretty much north, one of the fastest rates on the Earth. So why is all this important? Why is it important for us as humans, and why is it important to understand this for our work at GA? Well, firstly, plate tectonics is one of the major reasons why we have Earth hazards. And two of the main ones I'm going to talk about are, the first one is earthquakes and the tsunamis that earthquakes may generate. And if you have a look at this image here, hopefully you can see this, that all these circles, these sort of white or beige circles, are earthquakes with a magnitude greater than 6 that have happened since 2005 to 2015. And you can see they generally occur, a lot of them, well, most of them occur at or on these plate margins. And actually a lot of the earthquakes that form are actually forming at these subduction zones, where we're seeing plates being subducted beneath other plates here. So a good example is to the north and or New Zealand, and to the north of New Zealand there. Secondly, volcanoes or volcanic activity is again largely responsible from plate tectonics. So again, in these subduction zones, you're getting a lot of magma being produced, and again, this is a whole talk in itself. But you see a lot of magma production and volcanics being produced, especially those big explosive volcanoes at subduction zones there. And a good example is where you have the Nazca plate, which is a bit of oceanic lithosphere being subducted beneath the South American plate there, and the magmas being produced form a long line of volcanoes in South America. So you can see that Australia is pretty much surrounded on 3 sides by those natural hazards, all generated because of the action of plate tectonics. So natural resources. A lot of the work we do is in natural resources, whether it be minerals, oil, gas, things like carbon sequestration, geothermal power as well is important. Now, plate tectonics, like I said, generates or helps generate a lot of these magmas or hot rocks beneath the surface, which often drives groundwater and produces what we call hydrothermal fluids, which are one of the main agents of extracting, transporting, and concentrating a lot of the precious minerals and metals that we extract from the earth and require for building various things. So, for example, gold, silver, and copper, a lot of those precious metals are formed ultimately from the action of plate tectonics and the magmas they produce. Secondly, plate tectonics often is able to produce what we call sedimentary basins. So big sort of areas that we can accumulate big thick piles of sediments that are really conducive for forming things like fossil fuels that we can extract. But also these same areas can be really good places potentially that we can sequester things like carbon dioxide into those similar rocks. And then finally, for natural resources, again, those hydrothermal fluids from hot rocks and hot magmas can be harnessed things like geothermal power within and on the surface. So at places like Iceland, for example, most of their power comes from these from geothermal power, from ultimately the actions of plate tectonics producing these hot magmas and hot rocks and hot fluids beneath the surface. So finally, it's quite topical at the moment. We talk about global positioning. So again, if you have a look at this map here, you can see the general sort of forms of some of these movement of plates on the Earth. And it's really important to understand how the plates are moving and how fast they're moving, because this has a big impact into things like global positioning. So whether this be through handheld devices or things like GPS units, driverless technologies like that, it's becoming much more important these days to become as highly precise as we can with where we are on the Earth and how it's moving. And you might have read a lot of articles recently featuring Dan Jackson and his team about coming up with a new datum or a new reference frame for where we are in the world in Australia. And that's because the last datum that came out was in about 1994, and since then Australia's moved around 1.5 metres. And this is one of my favourite images on the BBC website, which is actually we've moved about the height of a kangaroo. It's really important to, I guess, to get across to you also that plate tectonics is not a sort of a closed science. We know a lot about it now, but there's still things we don't understand. Like in a lot of sciences, it's an evolving process. So things like what's going to happen to the configuration of plates in the future is a bit of a hot topic. And also what happens to those subducting slabs when they go down into the mantle is another area of research. You know, do they completely melt as they go down? Do they form some sort of slab graveyard and they just sit there for a while? And if they do, what location is this? So we're generally updating our knowledge on plate tectonics as we go. I just want to leave you with one of the models that we think, this is one of the reconstructions or projections that we think will happen to the Earth in the next few hundred million years. So again, it's a similar form to the video before, and see if you can see what happens to Australia in this particular model here. Okay, so you can see that we're going to initially become much closer friends with our Southeast Asian colleagues and friends. Yep, so like I said, there's some activities and some props to have a play around with after the talks. But in the interest of time, I think we'll stop there. Thanks a lot.
So, thanks, Chris.